So I'm going to select the topics. Actually, I'm going to go first through AVL trees. Then we're going to go through Heaps, then Bitwise Operators, and Summations. And I guess we can do sortings last. But I'm going to do a couple of each. So let's start with AVL trees. They seem to be like the easiest topic for people to get down. So I'm going to start with the simple insertion case. So let me skip through. Okay, here we go. So I'm going to give a little intro into what it is, like what the whole thing behind AVL trees is. So the whole idea is that when you have a regular binary search tree, it may be unbalanced, meaning you might have something that looks a little like this. And it's not going to be efficient because on average, let's say you have n equals 5, you're going to be traversing to get any of these values around n times. So it won't be exactly 5 times, but it's going to be just about when it's a skewed type of tree. So that's where AVL trees come in. And okay, didn't mean to go to white one, but okay, so that's where AVL trees come in, where you have a balanced binary search tree. So the whole property is that no two subtrees can be of an absolute value of 2 between the heights. So what does that mean? So let's say we have this tree that we have on our left. So we have 10, then 20, then we have 12, 12, and then we have 17 here. So notice how, so whenever you have a null case, so I'm going to draw the little nulls. Now you have these null cases, that's going to be a height of -1. So you can think of -1 here, -1 here. And the whole property to find the height of a tree is you take the maximum of the left and right and add 1. So that means that on this side, the right of 10 is going to have a height of 0. And on this side, you're going to have a -1. You're going to take the maximum of these two values and add 1. So it's going to be 0 plus 1 is 1. And same thing on these sides. So -1, -1, 0, -1. Take the maximum and add 1. So we're going to have 0 plus 1. And now at this point, we're at a fully balanced tree. So the difference between two values, its left and right, can be at most equal to 1. So if it's ever greater than or equal to 2, then you have an imbalance, and that's when you're going to have to restructure the tree. So in this case, let's see if we have to do something like that. So I'll just run through it again. So we're going to see what's going to happen if we're inserting 19 into the AVL tree. So if we're inserting 19 into the AVL tree, let's take the height. Or actually, let's insert it first, and then we take the height. So 19 is going to go to the right, then we're going to be at 20, we're going to go to the left, and then we're going to go to the right of 17, meaning that 19 is going to be added on this side. We still have our null here, and we still have our nulls here. So this is going to be -1, -1. We're going to take 0, which is going to be the maximum of the 2 plus 1. We're going to have a -1 here. Take the maximum of the 2 plus 1. And this is going to be -1, max of the 2. Oh, actually, right here is where we're going to have the issue. So notice how the difference between these two, the absolute value is 2. So to get from -1 to 1, there you have to make 2 jumps, essentially is what it is. So whenever you have that case, that's where you're going to want to restructure. And the way you're going to want to do that is you want to get it into a format, and I just call it the BAC format. So whenever you do insertion or restructuring, or even if you're doing deletion, you want to get into the BAC format. So A is the smallest value. So A is the smallest value. Wherever you have you're going to take the 3 values from wherever the imbalance was found. So right here, down the way towards where you inserted the value, including that value. So If the imbalance is here, we're going to see, okay, what did I add that caused the imbalance, and on which direction, like what path was it? So it was on this path right here. In this case, we're going to perform a rebalance, and we're going to choose our B, A, and C from these three nodes. So what that's going to look like is A is going to be the smallest of the three. So this is your A. B is going to be the middle of the three. So like the median. So this is the median. And then C is the biggest one. And now you're just going to put these nodes in the BAC format and then reconnect it back to the tree. So what that will look like is 16, then 10, then 20, or sorry, 12. And then right here, we're going to have B, 19. And then to the left, we're going to have A, and to the right, we're going to have 20. And notice how the property of binary search tree is still valid. So everything to the right of 16 is greater than 16. And yeah, everything to the left and to the right of 19 follow the properties. And we can also look at the height balancing. So we had the imbalance here. And now if we do the same strategy, so we're going to draw the nulls. So -1, then take the maximum of the 2 plus 1, and then same thing here, plus 1, and then now we're going to have 0, 0. So this is fully balanced right now. Let's just check the rest of the tree for any imbalance. If there's any, there won't be, but let's just check. So we're going to have 0, -1, take the maximum, add 1, and oh yeah, I hadn't done it for this side, but take the maximum of these 2 plus 1, and we're fully balanced. There's no case where we have an absolute value difference of 2 or more. So this would be the final tree right here, the one that I drew at the bottom. So that's the final tree. Now we have another question, and let's see what it says. Okay. So in a binary heap of 100 elements, how many elements are at depth 6, the lowest level from the root of the heap? The depth is the number of links that have to be traversed from the root to be able to reach it. So let's write this information down. So we have a heap where we have 100 elements. And we want to see how many at depth 6. How many at depth 6? So when it says the number of links, it just means, think of these lines right here. So if you have 1, then 2, then this is going to be at a depth of 2. So really the way depth works is, unlike height, you go 0, then 1, and then 2. But you can just think about it of the number of links you have, which is 1 and then 2. And then this would be everything at depth 2. So yeah, it looks like we're not going to have that much time before the answer comes. So I'm just going to close this up. Meantime. Okay, so let's think about the properties of the heap. So this is one of those type of questions where it's more theoretical. So don't feel bad if you get this wrong or you don't know how to approach it. But one of the properties of a binary heap is it is a complete tree. So what that means is that for every level, so let's just draw a simple little tree. For every level except the last level, all nodes are there. So possibly the last level might not be full. So what might an example be? This can be a complete binary tree because this is one level right here. And then this is another level, but all the nodes are there. Alternatively, you can also have it such that the last level doesn't have every node in there. So for example, this would also be another complete binary tree because all the levels except possibly the last one have the full number of nodes that they should have. So these right here are completely full. Every node is not missing. So another example, and by the way, this has to be done left to right. It can't be something like this. They have to be in sequential order from left to right. So I'm sure you guys have seen this type of structure in your heap where whenever you're inserting, you add here, and then you do your operations and whatnot. But you go in sequential order like this. So this is another example. Just remember, every row is full except possibly the last one, but it could be full and it would still be good. So if you have 100 elements, let's think about how we can calculate how many can be at the 6th level and also how many can be before it. So let's just take this example right here. And let's say we want to find how many nodes are at a depth of, 1, 2, 3. So let's say at a depth of 3, right? And right here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. So at depth 3, and we have 10 nodes. 10 elements, and the values don't matter, but so we want to, since we know that every level except the last one would be full, we're going to want to find a way to calculate that based on whatever depth they tell us. So they say a depth of 3 in this example that I'm giving you. So to be able to calculate what you have here, you can take 2 to the power of the depth, 2 to the power of the depth minus 1. So this will give you, whenever you have a full or a perfect binary tree, which is what this is going to be. This subpart here is a perfect binary tree because everything is there, and this is the formula that you can use to calculate how many nodes are in a perfect binary tree. Meanwhile, if you have a complete, that's going to be this whole entire thing. So that might be a little confusing, but this right here is perfect because there's nothing missing at all. But this this one that I'm circling in purple is complete because everything is perfect except for possibly the last row. So if let's just plug these numbers into the formula. So we're really calculating the number of nodes in the blue with this formula. So this will give us number nodes in blue. So if you do 2 to the power of 3 minus 1, that'll give you 8 minus 1, which is 7. And let's count how many we have here. 1, 2, 3, 4, 5, 6, 7. So that's good. We have that. And now, since we've calculated everything up until the last row, which could be full, could not be full, now we can just take the total number that we have. We know that there's a total number, and then based on what we calculated here, we can just subtract this out. So we're going to exclude this perfect portion that you can calculate with the formula, and we're just going to want to find the other remaining nodes that we can have. So that would be 3, and that'll give us our answer. So let's plug that into the question that we had. So we had heap with 100 elements. How many at depth 6? So what this is going to be is 2 to the power of 6 minus 1. Actually, let me rewrite this a little. So if they give us the number of elements, you can take number of elements minus 2 to the power of d minus 1. So this will be 100 minus 2 to the power of 6 minus 1. So this will give you 100 minus 64 minus 1. 100 minus 63, and then that's going to end up giving you 37. So that means that at the very last row, we're going to have 37 nodes. So I hope that makes sense. I hope that makes sense to you guys. It was a little bit confusing, but it just, the answer and like deriving the answer is completely based on if you understand like how a heap is structured, the fact that it's complete. Everything except the last level could be full, or everything except the last level has to be completely full, except like the last level, like I said. And that's how you can calculate it. So yeah, you can just remember this formula. I seriously doubt a problem like this is going to come up because this is the only one that I've seen of this type. So yeah, but it's still good to know. It's still good to know this. So number of elements minus 2 to the power of the depth minus 1. All right, so let's check out what the answer was. Okay, so let's go to the AVL one first. So they had 16. I know it's really hard to see, but they had 16 at the top. To the left, they had 10. To the right of 10, they had 12. And then to the right of 16, they had 19. To the left of 19, they had 17. And then to the right of 19, they had 20. So that's good. It's 5 points. And then part B, it is 37. So yeah, it's just like they said. The structure is always a complete binary tree. Thus, the number of nodes at depths 0 through 5 are 1, 2, 4, 8, 16, 32, respectively. So that sums to 33. So this is this part of the formula. And then they ended up subtracting out, and then that gives them the final 37. So yeah, it comes about observing the heap structure and knowing those little things about it. Again, some of this probably won't come up, but let's go on to the next question. All right, so I'll give you guys a couple minutes to work on this. So I'll come back at when the timer's at 7:30. All right, so it's 7:30. So they say, show the result of inserting 37 into the following AVL tree. So let's just draw it out. So just real quick, we don't have to check if it's balanced because, like they said, the following AVL tree, for it to be an AVL tree, by definition, has to be balanced. So we don't have to check the levels just yet. Just insert. So I'll do that in blue. So we're inserting 37. So start here, go to the left, go to the right, and then go to the left, and then we're going to go to the right. We're going to add it right here. It's going to have 37. Okay, and now we're going to see what we're going to have to end up doing. So this is where we're going to start doing the balance checks. So I'm just going to draw these X's. So this little area, if we have to do it elsewhere, we'll do it. But I'm going to have -1 because height at null always starts -1. Take the maximum of the 2 plus 1, so 0. It's going to be -1. And take the maximum of the 2 plus 1. And this is going to be -1. So right here, we have our issue. We have an imbalance. So like I said before, BAC, let's choose our B, let's choose our A, and let's choose our C. So our A is going to be 30, the smallest. Our B is going to be the middle element, and then C is going to be the maximum element between the three. And now we're going to end up with, let me just erase this. So BAC would just look like 37, 30, 39. Okay, so this is after the rotation. And by the way, that's just a regular rotation right there. Actually, let me see. This is a double rotation. So I just want to clear this up because there's some questions that will ask you if it's a double or a single rotation. A single rotation is when you're going to be rotating something that looks like these two. So just straight lines. If you're rotating this into the BAC format. Meanwhile, if you're doing a double rotation, it's literally just something that looks like this. So I guess you can call double like crisscross, like go this way and then this way. And then the single is just going to be straight. So that's how you can remember if they ask you specifically. But yeah, this was a double rotation case. And now that we did the rotation, let's just make sure we're all good. I'm sure you guys can probably tell, but let's just make sure. Let's make sure we're all balanced real quick. So -1, -1. I'm just going to speed through it because I'm sure you guys get the idea by now. Okay, so let's just look. No imbalance, no imbalance, no imbalance, no imbalance. There's no imbalance, so we're all good. The difference is at 0 or 1. It's not greater at all, so we're good. So that's going to be the final tree. So we're going to have 84, 25, 12, 37, 30, 39, 106, and 212. All right, so let's go on to the next sections. Okay, so we have give the best case runtime for inserting an element into AVL tree with endnotes. Okay, so the runtime for AVL tree is always log of n. Doesn't matter what you're doing. It's always log of n. So this is going to be log of n. This is going to be log of n. Worst, best, average, they're all log of n. So that's easy to remember. Best case inserting a element in a binary tree with n nodes. So this is one of those questions. I mentioned this before in a previous review. For some reason, they flip-flop between O of 1 and log of n. On average, it would be log of n. So I just want you guys to know that. But best case, I assume, is when there's just nothing in the tree. But there's been some times that they've been inconsistent with that. So whatever, just go with either O of 1 or log of n. I believe for this one, they're going to say O of 1. But yeah, average case is usually log of n, and then the best case should be O of 1. So big O notation, give the worst case runtime. So the worst case runtime is if it's a completely skewed tree. So just like what I had mentioned, if it's like a straight line, then on average, you're going to be you're inserting something. You're going to have to iterate through, around n nodes, depending on what you're inserting, of course, but it's going to be skewed on one side. So that's going to affect your runtime by a lot versus if at every decision, like in a tree like this, let's say you want a value that's on this side, or you're going to be looking for a value on that side. When you make this jump, you're invalidating half the tree. And then let's say you want to go this way, you're invalidating half the tree. So that's the logarithmic behavior because you're dividing by 2 each time. Meanwhile, in this, there's no division really. So just O of n. Yeah, there we go. So answers, that's good. That's exactly what we had. And log of n, O of 1, and O of n. So yeah, average, log of n, best is O of 1. And it's weird because normally they tell us not to think about things in terms of like smaller cases, but for whatever reason, they want you to think of it for binary search tree across the board. So, all right, so let's go to the next question. Okay, so it says, let me just make sure what this other part is. Okay. So create an AVL tree by inserting the following values in order, 42 and so on. Show the state after each insertion, draw a box around each of these 8 trees. So I will let you guys work on that until about 7:30, and then I'll hop in to explain. All right, so let's start. So the numbers they give us are 42. So I'm just going to start and go in order. So just write them out real quick. And 59. Okay. So, yep, got all the numbers. All right, so we have to make 8 trees. And yeah, make sure you draw a box because if not, you're not getting points because then they don't know what step you did and whatever. So at the start, you have one element. Really, the first two elements, they're easy points because there's no balancing required. Because if you think about it, this is just 0 and then 0, and it's complete, or sorry, -1 and -1. The difference is not greater than 2. It's just going to be the same. So this is good right here. Then when you go on to add the second one, it's going to be the same case because you're going to have 42, 68. So this would be -1, -1, takes the max 0, and then -1. So there's no way you can have a difference of 2. So you can just draw those two right off the bat. That's some of the points right there for you. Now let's go on to add 35. So if we add in 35, that's where we might have an issue. Oh shoot, my bad. I put the tree wrong. There we go. And so 42, and we have 68, and now we're gonna add in 35. So 35. So at this point, we're good. We don't have anything to do here because -1, -1. So we're all good. Now we're going to add in 1. So let's just confirm that we're all good. So -1, -1, 0, -1. We're good here. Then take the max of the 2, add 1. And we're going to do -1, -1, bring up a 0. So we're still good. So far, easy points. And yeah, just make sure the properties of BST are maintained, so you don't mess up kind of like how I did a little there. So we're all good so far. Now we're going to add in 70. So I'm going to calculate the same thing. We're still good. And now we have to add 25. So I'm just going to copy these trees. So 25, that's going to go, we're going to go down to the left. So we're going to be here. And now we're going to go to the left again. And now we're going to add it to the right of 1. And this is where we're going to have our first imbalance. So that would look like it's going to have a 25 here. And let's just take the calculations again so you can see why. And I'm not drawing the X's, but make sure, I think it would be a good practice to draw the X's just so you remember they exist. Sometimes you might forget. So right here is where we have our imbalance. Remember, it's 2 jumps, so difference of 2. So since we have that imbalance there, we're going to want to choose our BAC of these 3. So our B, A, and then this is our C. So what that's going to end up looking like is 25 at the top, and 1 to the left, and 35 to the right. So this is what I end up looking like. And we can take the calculations again. Still good. Now we have to add in 79 and 59. Let me just check what the time is. Okay, we have just a little bit of time. Okay, and let me just write this down. So we have to delete 59. Okay, and then delete 59 or 79. All right, so let's insert 79. So we insert 79, it's going to go to the right here. And let's just check if we're good or not. So let's draw our X's. Let me choose a better color so you guys can actually see that. Take the max of these two, add one. So there's an imbalance right here. And like I said, BAC. So you see these problems, they follow the general pattern. So this is going to be the last one that I do. And deletion is going to be very, very similar. We're going to do actually a deletion in this problem, and then we pretty much wrap up AVL. But we're going to imbalance. We're going to have, let's choose our BAC. So this is going to be, so this is a single line. This is a single rotation, not a double rotation. And it's easy to choose our ABC in this one because since it's all right-sided, it goes A, B, and C. So, and on this case, if it was on the opposite side, this would be C, B, and then A. So I hope that makes sense why. So we're going to end up with 70, 68, and then 79. So this is what we're working with now after we insert 79. Now we're going to insert 59. Oh, great. Now the whole thing did. Okay, so now we're going to insert 59 into this tree. So that would end up happening, go this way, go this way, go this way. We add on 59. And let's just think about it. We don't have to do all these calculations. Once you get good at it, you can start to tell. But just think about it. If we were good at this stage, what would be the maximum height imbalance? So the maximum height imbalance would have to happen between these two subtrees right here. And what is the level difference? It's just 1. And it's 1 is not greater than 2, greater than or equal to 2. So we know that we're good by inserting. You can probably tell by just looking as well. So I'm not gonna, do the numbers again. So we're good with that. So this is gonna be the final state. This is 8. So let's just count and make sure we have 1, 2, 3, 4, 5, 6, 7, 8. So we're good. And now what we have to do is delete 79. And I'll show you why I said that it was very, very similar when you're deleting. Okay, so this is for deletion. So if we delete 79, we're going to end up removing this node. And we're just place a null right there, okay? So we're going to place a null. If we place a null, that means that this side goes from what it used to be. So this used to be -1, -1. You pass up a 0. So the right side of 70 has a height of 0. But if you have a null there, the right height of 70 is actually going to be -1. So now we have to set this first before we start calculating. And now we can look at the rest of the tree. So I'm sure you guys can tell there's not going to be an imbalance right here. There's going to be an imbalance right here. So let's see why that is. -1, -1. bring up the max plus 1, 0, -1, then max plus 1. So we're going to have 1 and -1, and this is where your imbalance happens. And again, BAC. So this is going to be C, B, A, and we just got to move it around. So I'm going to have 68, 59, and 70, and that is deletion right there. There's some more complicated cases, but they're not going to make you do those complicated cases for the most part. This is pretty much what most deletion is. They don't really have that many deletions. Typically, just insert these values and end up showing each step. So let's check our answers. Okay, so we had 42, 42, 68. Third one is good. Fourth one, it's also good. Fifth one, good. And this star right here, they're not necessarily saying that this is one of the trees you have. They're just saying that, okay, we know that there's an imbalance here. We're going to rotate it. So the one you would have circled or drew on your paper is the final. So this one right here, which is the one that we ended up drawing right here. So this is 6. And then 7 would be this one up here. So 7. This is good as well. And 8. So this is the final. So that's 8 points out of 10 right there. And they only give you 2 points for deleting. So let's see what they ended up with. Exact thing, same exact thing. So it creates an imbalance at 70, which is what we had right here. So yeah, when it comes to deletion, you delete the node, calculate the height after deleting, which if it's a leaf node, it's going to be -1, and then find the imbalance and put it in your BAC format. You remember BAC, you can answer all these questions. And if you remember like the whole -1, take max plus 1, you can answer all the AVL questions. All right, so we're going to move on from AVL trees, and we're going to end up doing, let's see, what's the next topic? Let's do some heaps. Okay, so I'm going to start the timer, and it looks like it's just 5-point question. And I'll give you guys until about 7:30. All right, 7:30. So it's saying show the state of following min heap after performing the delete min operation. Instead of writing this with a pen or pencil, typing the result in text similarly to how the drawing. Okay, wait, never mind. That has nothing to do. Okay, so let me get the whiteboard out. So they're telling us to do the delete min operation. Okay, so this is our min heap that we're working with. And delete min is just deleting the top element, so removing it out of the tree. So let's say you have a box. You want to take this element, put it in your box. You're going to store it, take it away from here. And now that you take it away, you're going to be like, okay, what am I going to put in placement of there? So what you're going to do is take the element at the bottom level all the way to the right. So this is kind of like what I was talking about, like the binary tree when it was asking the 100 nodes and the depth, how the last level is not always going to be completely full. It could be, but it may not be. You're going to want to go all the way to the bottom and go all the way to the right. That's the property for binary heaps. They're going to be added in order of left to right. Like this, you won't have something that's like added like this. It's always going to be this way and then this way. So what you're going to do, you're going to take this element, bottom rightmost, and just put it up here. So let's delete this right here. And the whole idea is that you're going to swap the two. So that means 90 would end up 90 would end up going here, and 14 would end up going here. But in the structure of the code, you're gonna pretty much end up saying that the size ends at this point. So you're technically ignoring this because the next time you go to add something, you're gonna overwrite this value. So just think of it as it's not there. So I'm just gonna delete it. So we're gonna ignore it. And this is technically what we are working with right now. So at this point, we want to best preserve the min heap property as we insert. So now we have this value. And if we think about what a min heap is, just looking at this without doing any operation except the swap and the removal, we're going to say, okay, it's not a min heap. The property of a min heap is that for every parent, it is smaller than both of its children. So 90 is not smaller than both 22 or 72. It's not smaller than either of them. So you're going to want to choose the smaller of the two children and swap towards that direction as you go down the tree. So what do I mean by that? We're going to look at our two children under 90, which we're going to start here in yellow. We're going to say, okay, which is the best two ways I can go? Let's pick the minimum of the two and let's go down that way. So you can think of it like we're going to swap these two. So we're going to end up with, right here, we're going to have 90. This is going to be 22. And now at this point, we're going to see, are we good? So is everything under me, is it smaller? So, okay, so 90, and then we're going to see, or sorry, is everything under me, is everything over me bigger? So at this point, we're going to say, okay, we can swap down towards one of these to choose the minimum. Because we haven't satisfied the property, the two things under us are not bigger. So then we're going to place 90 down here. My bad, I had gotten a little confused, but I'm going to have 38 right here, 90, and then 40. And now at this point, let's just analyze the tree to make sure we did this correctly. So 38 is smaller than both of its children. So yeah, we've done that. So is 28 smaller than both of its, is 22 smaller than both of his children? Yes. And is 72 smaller than all of his children? Yes. So at this point, we're good. So yeah, sorry if I might have messed that up a little, but I meant everything under us has to be greater. So the element that you're currently at has to be smaller than your two children. But your two children, if you think about the opposite case, your two children have to be greater than the element you're at. So yeah, you can just think about it either way, but I like to think about it as the parent is smaller than both children. So there's going to be the final min heap after deleting. So let's check our answer. So 22, 38, 72, 90, 40, 80. So yeah, that's good. All right, let's go on to the next.
Well, if you don't mind me asking a question, for when you swap, when you're doing max heap instead, right, and you're doing delete max,
yeah,
is the rebalancing or rekeeping the heap property different?
Yeah, it actually is. It actually is. So what was happening was I was like, I had like gotten confused between the two for a second, so that's why I had messed up. But when it comes to a min heap, if you're at a given node, for again, min heap, it has to be smaller than both of its children, right? So that's for a min heap. Meanwhile, in a max heap, you have to be greater than both of your children, because the whole idea is the higher you end up going. So let's say you have a min heap, or sorry, a max heap that kind of looks like this. The higher you end up going up the tree towards the root, the bigger the value is going to be. So that would mean, let's say, let me just draw a max heap real quick so you can see the example. Okay, so in this case, we have a max heap. So everything is smaller, or sorry, everything is greater than its two children. So in this case, when we had a min heap, 38 is smaller than both of its two children, and same thing for every other node if it has children. And in this case, 50 is greater than both of its children, 60 is greater than both of its children, 100 is greater than both of its children. So this is a max heap. So if we were to delete in this one, so we would end up with putting 12 up here. And in a min heap, when you're deleting and you're going down the tree, what's going to end up happening is you're going to choose in a min heap. Again, in a min heap, you're going to want to choose the smaller of your two children and swap down that way and keep going in that direction if you can. Meanwhile, in a max heap, which is what I'm drawing right here, is you're going to want to choose the maximum of the two children you have and swap that one. So, because just think about it, if you want a max heap, you want to get the maximum as high as it can possibly go, which is why in a max, you're swapping with the biggest one of your two children. Meanwhile, in a minimum heap, you want to preserve as high up the tree. Since you're going down, whatever you swap with is going to end up going up. So you're going to want the smaller thing to be at the top in a min heap, but the bigger thing to be at the top in a max heap. So this would end up looking like 60. This would be 12. And now we're going to see, okay, is my child bigger than what I am right now? So yes, so we're going to end up having 53 here, and then here we're going to end up having 12. So that's the only difference.
Okay.
It's just a very minor difference.
Yeah, it is. All right, that's good to know.
But you always get the rightmost child?
No. You get
initially?
Oh, yeah. Initially, you're going to go all the way to the bottom level. So all the way here, and then go as far right as you can, and then swap that one upwards, like with the root of the tree.
So heaps don't necessarily follow the like BST rule.
No, not necessarily. Not
Okay.
necessarily. No.
That's why. Okay, because I was confusing that deletion with like go rightmost node and get the leftmost. Like you do with the BST, because I know.
Oh yeah. It's completely different because like let's say if you insert in a let's just say a min heap, for example, then you can insert 60, and then you can insert 100, and then you can insert let's see 120, and this would be valid because it's minimum. So 60 is smaller than both. So, but it doesn't follow the property because in a BST, both of these would end up being to the right.
Yep.
So yeah, they don't follow the same. They seem like they might, but they really don't.
Yeah.
Yeah.
That's good to know. Thank you.
All right. So heaps /hash table. Where's the? Oh, this is one of those questions. When I made this website, there were some questions that they had nothing to do with heaps, but they just had heaps in there. So I'm just gonna skip this one. I don't know why they said it had heaps, but just hash table question. We already did those. Okay, so let's do this one. Give you guys some time to work on it until about 7:30. Okay, I didn't realize it went past. Okay, so let's hop into this one. So we have an array implementation. The min heap contains exactly 8 integer values without any duplicates. The min heap does not contain the value 14. Inserting 14 into the min heap would cause us to incur the best case runtime for insertion. So for the best case runtime, whenever you're inserting, is that the value never moves. So the whole idea is when you insert, let's say you insert something right here, you're going to end up swapping up until you can't swap up. So that would mean that whatever element that you're considering, so if you're right here and you're considering swapping with this one, if this element right here is smaller than the one that you're looking to swap with, then, or the one that you're currently at, then you wouldn't perform that swap, and that's where you would stop. So really the best case runtime is if it requires no swapping, no movement up the tree at all. So we can think of that like very simple case. 8, so we have 8 values. And if we insert, say we insert 14 right here, then since we're trying to preserve min heap property, the parent of 14 is not greater than 14. So then you're just going to stop right here because we're using a min heap and we want the smallest element to be up top. So you're just going to stop right here, and that's going to be the best case right there. As for the second part, it says we have 8 values, no duplicates, does not contain 98. And 98 would incur the worst case possible runtime for insertion. So the worst case possible runtime, there's different ways for going
Wait, are
about.
we gonna for this one, do we have to put values in for the array that would just so essentially we would have to have everything above 14 smaller than 14? Or is it just the parent has to be smaller than the children? Is that the only rule?
Wait, say it again. Sorry.
So for there, like to fill in the array, what numbers would we use in case like to
Okay, I got you. So I forgot to mention this. Whenever you're thinking about the array, so you can look at it from the order that I wrote them down in. So at index 1, you would put whatever values here. So I know I put 1, but this could also work. Let me just write it like this. So I could have like 3, 4, 5, 6, 7.
Oh, okay.
Yeah, so this is 1, this is 2, this is 3, and so on.
Oh, okay. So you can use those actual numbers like that because that follows the min heap property.
Exactly.
Oh, and 14 is okay to fit right under 4 because 4 is smaller than 14.
Mm-hmm. Yeah, exactly.
Oh, wow. So you could have just did, yeah. All right, that's cool.
Mm-hmm. Yeah, it doesn't have to do with the indexes. So let's go on to the next one. So the worst case possible runtime. The worst case possible runtime is going to be, you actually have to go through the tree. So that's going to be logarithmic. And that's pretty much going to be where you're going to have to travel all the way up to the tree, to the very top of the tree. So let's say you insert, remember we insert at the very bottom. So if we insert, let's say we have something like this. If we just inserted an element right here, what it would look like to have the worst case is we would have to end up putting something at the root. So that would be our worst case. So we would pretty much, if we're trying to increase the worst, we're going to want to go all the way up to the root. And we can do that easily by choosing a value, choosing every number to be greater than 98. So let's see, we can do 100. Actually, let's choose a better number. 105, 110, 115.
Would the best case of inserting in a heap still be log event as well?
No, it would just be 1 because this one right here, we didn't move anywhere. So
okay.
Yeah. Okay, so we're gonna have. Oh, they say no duplicate values as well. So. Okay, so 1, 2, 3, 4, 5, 6, 7. And then let's do, doesn't matter, 140. And if we insert 98, what's going to end up happening is we swap here. So now we're going to have 98. It's going to be 120. We swap here, 110, 98. We're going to swap here. So it's going to be 105, 98. And now we have everything preserved. So that would be, just draw it out quickly. 115. Then we're going to have, I believe it was 110. Then 140, 120, then 130. Oh, shoot, what did I just do? So 130 and then 135. So we're still all good with the properties. So 1, 2. So these are all numbers that are good. Let's see what we ended up having. So we ended up having. Now let's just draw what they had. So they had 1, 2, 4, then 12. 1, 2, 4, 12, 9, 7, 6, 16. So again, if they inserted here, 14, it wouldn't move up. And same with this case right here, it wouldn't move up. So we're good there. And let me see.
So in that case, it only needs to be the parent of 14 that needs to be smaller than it. Or greater than it, sorry.
Well,
No, smaller.
it would have to be everything else, because if not, then you wouldn't have this case right here. If that makes sense. Like, for example, 2 has to be smaller than 12, and by that being the case, then 12 would be smaller than 14.
Yeah, you're right. Okay.
And so on.
All right. But our
So-
original, like the way we wrote it was still correct, right?
Yeah.
Okay.
That's good. So 98 at the top. Oh, wait, this is actually when I was moving everything up. So I had 105. Let's just see all their values. All their values are at a greater. So let me just redraw this tree that I had drew. So 105, 110, 115. And what else did I have? I had 140. And we inserted 98 right here. So this is where we inserted 98. And the tree that they had was 101, 102, 112, 109, 107, 106. And the last one was 116. So if you ended up inserting 98 right here, you would have to end up swapping all the way up. And then eventually 98 would sit at the very top as the minimum. So yeah, good point, because I didn't think about it too much, but yeah. So for 14, it would have to be less than 14, but then for 98 to move all the way to the top, everything would have to be greater than it. And that means that 14 cannot end up being like under 98 at any point. So that does make sense. My bad on that one, guys. All right, so let's go on to the next heap question. So we'll just do one more. Or actually, this one, I'll end up going through it right now, because this is another one of the insert cases, which we just did a couple of them right now. So it shouldn't take too long, and you guys should be able to get it. So it says store a minimum binary heap, draw the tree version of the corresponding binary heap, then remove the minimum value as shown and show the resulting heap in tree form. Index 0 isn't shown because index 1 stores the value at the top of the heap. Okay. So pretty much you just go the same way. Start at the top, then go down, then go left to right. So let's start with the values 2, then 16, then 3, 22, 17, 12, 13, then 23, 30, 18, and then 20. All right. So that's what we're working with. And we're going to remove the minimum value. So we're doing delete min operation. So we're going to end up removing this value right here. And we're going to get the bottommost, rightmost value. So this one right here. So let's swap these two. So this 20 is going to come up. That's right, 20. And then we're going to end up removing this one and forgetting about it. And now at this point, we're in a min heap, remember? So we're gonna choose the minimum of our two children, assuming that 20 is not smaller than our two children, meaning it wouldn't be like the top, which it'll never be. Then what's gonna end up happening is we're gonna choose our smallest child and go that way. So this one's gonna end up becoming 3. It's gonna end up becoming 20. Now, at this point, we're going to choose our minimum, swap that way, and then we're going to end up being done. So it's going to be 20 and it's going to be 12. So what we're going to end up with is 316. Just end up writing it. So this is going to be our final answer. So let's just make sure the properties are satisfied. Two children of 3 are bigger. Two children of 16 are bigger. Of 22 are bigger. 17, and same thing with 12. So we're all good there. Yep, so it checks out. All right, so that was 5 points. You guys want to do another one, or you guys want to go on to another question? Or sorry, another topic. The other topics that we're going to end up doing, we did AVL, we did Heap. Okay, cool, another topic. So now we're going to end up doing is, you guys tell me, sorting. No, we already did tries. We did tries on the last session. The videos on, if you go to this website right here, I sent it in the bottom. Let me just send it right now. You can go to this playlist right here, SHPE UCF. It'll be to a YouTube playlist, and you can watch the video there. It was the most recent one. So out of the next topic, okay, sorting. Cool, let's do sorting. We're gonna do sorting, then we're gonna end up with summations and then bitwise. Okay, so let's start. Okay, so we're gonna end up doing bubble sort. And the way bubble sort works is that at any given point, you're gonna check if the value that you're currently at, if it is greater than the value in front of you, and if so, you're gonna swap. And you're pretty much gonna end up doing that through the whole iteration until you get to the very end. So what that's gonna look like is we're gonna start off at 6. This is gonna be for the first iteration. So we're going to start off at 6, and we're going to look ahead. Is 12 greater, or is 6 greater than 12? No, so we're just going to leave it there. Now we're going to be at 12, and we're going to see, okay, is 12 greater than 1? So it is. And now we're going to see here, we're going to see at 12, is 12 greater than 9? It is. And is 12 greater than 4? It is. And same thing with 2. So we're going to swap it. Now we're going to end up doing this process again on the whole array. So we're going to start from the very beginning, from 6. So 6 is greater than 1, so swap. 6 is not greater than 9, so we're not going to end up swapping. But then we're going to see that 9 is greater than 4. So we're going to swap these two. 9 is greater than 2. Going to swap these two. And 9 is not greater than 12, so we're going to leave this alone. Now at this point, at this point, 1 is good. 1 is less than 6. Then at 6, we're going to look ahead. 4 and 6, we're going to swap. 6 and 2, we're going to end up swapping. And then at this point, 6, 9, and 12 are good. So notice how the way bubble sort works is it ends up creating the sorted array on the right side. So a sorted part. So that's, I guess, one way you can tell if you're doing your bubble sort right. Meanwhile, something like insertion does it on the left, the sorted part. But let's say we've done 1 iteration, 2, 3, and we still have 2 more to go. So 1, I'm going to look at 4. So we have 4 here, but let's look at 2. So we would have swapped right here. We had 4, but then we would have swapped this with 2. And then after that, you can tell that you don't have to keep doing anything. And same thing right here.
Can you just leave it empty, or like, do you need to fill that last one in? If we're
I'm pretty
done?
sure that they would make you just write it. I would just end up writing it. And you end up stopping here because, so you don't stop here because you have 2 elements and you don't know if you're done. But then once you get to 1 element left, an array of, or at least a section of 1 element is always sorted. So that's why you end up stopping here. And then yeah, you don't check to include like the whole entire array. So you just leave this one part here and then you just stop. So that's why they only do 5 iterations. And let's see. So we have part B. So what is the best case and worst case for each? So we have merge sort. So one thing, merge sort, best case and worst case, average case, it's all n log n. So this is for all. Now, when it comes to quick sort, we have a best of n log n. But when it comes to for worst case, it's going to be n squared. So the reason it's going to be n squared is if you have the array in reverse order and you're trying to sort it, pretty much you're going to end up everything, since you're partitioning, everything to the left is going to be smaller, everything to the right is going to be greater. It's already going to be in that order, so there's nothing to end up partitioning that's going to help you like decrease your runtime. So you're going to have to end up, doing n squared operations to get it finally sorted. So worst is n squared. And then for insertion, your best is going to be O of n. And the reason that is because insertion, like I said, it creates an array towards the left that's sorted, because you end up putting stuff back until it has to, pretty much until it finds its spot in the array. And the whole idea is, since you're checking backwards, let's say you have something like 1, 2, 3, 4, 5. You're going to start here. You're going to check backwards and see, is the value behind me, is it greater than where I'm currently at? And you would say no. So it's just an O of 1 check. Same thing here, O of 1 check, O of 1 check, O of 1 check. And you're doing an O of 1 check n times. So that would be O of n best, just assuming the array is sorted. And in your worst case, you have O of n squared. And that would be the case. That's technically going to be the average case, but if you want to see the worst possible, let's say you have the opposite. So if you have 5, 4, 3, 2, 1. So you're going to have to end up, at this point, you're going to put 4 backwards. So 4 is going to end up going here. You're going to end up moving 3 backwards as far as it can go. This one's going to end up going farther. And the first one is going to be 1. So notice how you're going to have to do about n squared operations for all the number of swaps you're going to end up doing. You're going to do comparison after comparison after comparison until you get to the end. And overall, it's going to be n squared. So that's the worst case. So let's compare what we had. 6, 1, 9, 4, 2, 12. And yeah, everything else falls in line. It's good. Merge sort, all n log n, quick sort n log n, worst case for quick sort n squared, best case of n and worst n squared. So we're good there. So yeah, if you see, if this is bubble and you see that it's getting sorted to the right, you know that you're doing it correctly. Okay. So I'll let you guys work on this. All right, so let's get started. So the following diagram shows an initial array followed by what the array looks like after a single pass of some sorting algorithm. Indicate what sorting algorithm is being applied and give that algorithm's worst case runtime using big O for array of size n. Okay, so let's draw this out. Okay, so this is what they end up giving us. And we are gonna, after one pass, we end up with this right here. So with something like this type of algorithm, it's easier to tell than part B. I was just looking at them, but in this one, let's just note how many things have changed, how many things have changed place. So if we take note, we only see that we see that these things are all the same. Everything here is the same, right? And in blue, I'm gonna do what has changed. So these two have changed. So it's a sorting algorithm being applied. So let's think about what type of sorting algorithm does what it did here. So it looks like from this point where we were at, it looked further on and tried to find the smallest element that it could. And then what it ended up doing was it swapped it into place. So for those that know there's the sorting algorithms, this is classic selection sort. So selection sort, you find the index of the smallest element, and then you store that, and then what you end up doing is you just swap it with like whatever index you're currently at. So if you're trying to find the best candidate for index 0, you're going to look through the rest of the array, including this one itself, because it could very well be where you're currently at. And then once you find the best candidate, which would be index whatever this is, n minus 1, then you're going to swap it into place. And that's why you see everything else stay the same except that. So you can tell quickly that selection sort. Selection sort only moves 1 or 2 pieces at a time if a swap can happen. Okay, so that was that. So sorting algorithm being applied, we have selection, and the worst case runtime is n squared. So now let's look at part B. So in part B, we have 84, 19, 3. Okay, so now we also have 19, 3, 42, and then we got 91. Okay, so let's try and see what ended up changing here. So in this one, a lot of stuff ended up changing. So let's see what ended up changing. So we ended up changing what was right here. Also what was right here. Yeah, and you can see like a bunch of stuff pretty much ended up, almost a whole entire thing changed. So what type of algorithm has a behavior? So in one pass, if you think about, let's say, insertion sort, if you think about insertion sort, what it would end up doing, it would end up just shuffling a number over. So let's say we were at a number right here. So this is not going to end up happening, but I'm just giving an example. Let's say we had a number here that had to go backwards. What would end up happening, if it's going to, let's say it's going to end up sitting here, it's going to end up landing here. It would end up swapping this number here, this number here, this number here, and then end up at this point right here. So the things would just move over by one to the right. But in this case, that's not what ended up happening. So we can override insertion, right? So insertion is not it. We just see how much time we have. We have 2:30. Okay. So insertion is not it. Let's see selection. So did only one thing change? Or did only two things change? No, because literally the whole array changed. So selection is out the door. Then let's think about something else. Let's see. So this is 1, 2, 3, 4, 5, 6, 7 elements. So it's of a single pass. So let's think about bubble sort. So 84 ended up moving all the way until here. And then remember how what ends up happening with something like bubble sort is that things end up shuffling towards the left if they are smaller than the number you're currently at. So 84, let's say 84 ends up moving here, and we notice how 19 went to the left, 23 went to the left, 66 went to the left, all by one. But then once 84 got here, it stopped at this point. And then 91 was the one that ended up getting picked up and moved to the end. So remember, bubble sort, it checks this element versus the next element. And if this element, the element you're currently at, is not greater than the element to your right, then you're just going to stop. So that's why 84 ends up stopping here. And then at this point, you end up checking 91 against 44, which ends up moving it, 91 and then 44. And then you do the same thing for 42, and that's why 42 ends up here and 91 ends up at the end. So this is a classic case of bubble sort right here. Let me just see what the timer is at. We got 37 seconds. So this is 100% bubble sort. Now, this last section is actually recurrence relation, but I'll end up doing it. It'll be very quick, and I'll explain it. Hopefully going to do recurrence today, but whenever they ask you for the runtime of something like merge sort, this is always going to be what the runtime is. So 2t of n over 2 plus O of n. This can also be just n or O of n, it doesn't matter. But the whole reason is that you're going to have, remember the structure of merge sort code, you have two recursive calls that end up splitting the array. So let's say we have an array of size 4. You're going to have one call that ends up splitting this, going this way. And then you're going to end up splitting this and going one way. And then these are your base case when you have something of size 1. And likewise, you'll do the same thing on this side. So at every recursive call, you have two steps where you're dividing the array into two pieces until you hit the base case, right? And then at every point when you come back up from the recursion, you're going to merge these two halves. You're going to merge these two halves together, these two halves together, these two halves together. So this is the O of n step right there, and two recursive calls that end up dividing the array. So that's how you can derive that. So selection sort, n squared, we got that. Then we had bubble sort. Oh, I didn't say n squared for this one, but I'm sure you guys already know n squared. And let's see what they had. So t of n, 2t of n over 2 plus O of n. So that's exactly what we had. So that's good. So let's do one or two more of sorting, and then I'm going to end up going on to Bitwise, and then we'll wrap up with summations. So they want you to find out how many swaps you have to end up doing for insertion sort. So there's a quick way to calculate it, but I'll just run through it so you guys see how you end up doing the insertion sort. And for each iteration, I'm going to have a number of swaps that we end up doing. So I'll put the number right here. Just do 1, 2. It end up being a decent number, but we can end up running through it, which is what most people would end up doing. And so I can show you the algorithm. Okay, so the whole idea is you're going to start from here and look backward, or sorry, you're going to start from the first index, so index 1, and you're going to look backwards and see if you can swap. So pretty much you're going to see, is the element that I'm currently at, is it smaller than the element that I'm behind? So right here at 25, you're going to see, okay, 35 is greater, so swap it. So I'm going to draw a blue dot so you can see where we're at every given point, or where we're starting at. So yeah, we're going to end up just like this. And we're going to have a couple more, but so right here, we're going to end up going 1. So we're going to have 25, 35, and here. I'm not going to draw past this because we're only really changing this part of the array. So I'm only going to draw all up until the blue dots, because otherwise the rest would not be touched until later iterations. So right here, we're going to see, okay, where does 15 go? It ends up going all the way back to the start. 25, 35, and now we're going to have 29 here. So far we've done, I'm just looking at the jumps, so we can just count the jumps later on. So this one is going to end up being placed right here. 16, 25, 29, 35, and we can put 39 here. So 39 is not going to have to move anywhere, actually. And let me just extend these lines a little. Okay, so 15, 25, 29, 5, and 22. So let's see how many times we have to move back 22. So you have to put it here. So that's going to end up looking like we're just going to move all these over and place 22 right here. So 22, then 29, 35, and then 39. So we end up doing 1, 2, 3. And I'm sure you guys get the idea at this point, but I'm going to just finish it through. So now we have 19. So let's see where 19 ends up going. 19 is going to end up going right here. So we'll just push everything over by 1. Oh, sorry, what I ended up doing here. I put 22 accidentally in the wrong place. Let me just check how much time we have. 2 minutes. Okay. And the one that we were at was 19. So we're just going to place 19 right here. And the number of jumps we made was this many. Then 6. I'm not going to end up drawing this one out, but we're going to have to go all the way to the beginning. Right? So it's going to be where we're going to place 6 at. And then 21, we can just see where 21 is going to end up at. So 21 is going to end up at this location right here. So we're going to end up doing 1, 2, 3, 4, 5, 6. So this is for 21. So now right here, we can just count these jumps. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So we should have 26 for that. And then for this right here, average case runtime of each of the sorting algorithms in terms of n. So we have insertion sort. The average case is going to be n squared. Selection sort, n squared. So those two on average are going to be n squared always. For heap sort is one that people usually get tripped up on. But if you think about all operations on a heap, it's log of n time to insert, delete from a heap. But then if you have n items, so let's say you have n items, you put them into a heap, that's n log n. And then if you pull it out of a heap, you're going to do it n times to empty it out. And each operation is log of n. So your overall runtime for heap sort is just n log n, because you throw stuff into a heap, you throw n things into a heap, it takes log n time for each, and then you do the same thing, pulling them out. So that's n log n. Merge sort is average, always n log n. And quick sort's average is also n log n. So let's see, number of swaps. 25. Well, I guess I added 1 somewhere, but close enough. 25, 26. So everything else n squared, n squared, n log n, n log n, n log n. So we're good right there.
I'm gonna ask a question. With average case, are we assuming worst case is average case? Because those are also, well, no, I guess quick sort's not, because I get confused sometimes with average case, because like it's all right. Well, because the worst case is the same for all of those, right?
The worst case for which all?
For the insertion and selection sort,
Worst case for insertion and selection, yeah, n squared.
it's an average. So it's on average, it runs the worst. Is basically,
Yeah, for quick sort and selection.
okay.
Or so sorry, for insertion and selection, my bad. But quick sort, its
Has a
averages
worst-
yeah, it has a
oh,
worst
n.
case of n log n of
Yeah.
n squared,
N
my
squared,
bad.
yeah, n squared, yeah. But averagely it runs O of n log n.
Yes,
Okay,
on
so
average.
I just
And
wanna confirm
at
that.
best as well, because the whole thing is n log n is smaller growth than n squared.
Yep.
So that's why it's best and average and whatnot. But most of the time, you're going to do n log n on quicksort. The worst case for quicksort is n squared, but that's like on a very specific case when the array is reversed. So
Yeah.
that's not common, you know?
Yeah.
So yeah, that's that on those runtimes. I know it's a little confusing, but for the most part, like the easiest way is to just memorize them. And if there's any special things, like for example, insertion is O of n best case, you just have to know it's because if it's already sorted. So typically these like very weird edge runtimes, it's either sorted or it's sorted in reverse order and you're trying to sort it. So that's how you can think about it. Insertion, the weird one is best case, O of n, it's already sorted. And quick sort, the worst case is it's sorted, but in reverse order. So it's in descending order. And then that'll give you n squared. All right, so I'm going to do that for sorting. That's going to be it for sorting. Let's go on to bitwise, and then I'll end up with summations. So let's do some Bitwise questions. Okay, so I'll give you guys on this one, I'll give you up until 7 minutes left. All right, so let's start. So it says, imagine a dating website that asks you 20 yes or no questions and store the answer in a single integer between 0 and 20, or 2 to the power of 20 minus 1, with the answer to the kth question stored in the bit 2 to the k minus 1, with the bit 0 representing no and bit 1 representing yes for the corresponding question. So if somebody answered 1, 3, and 4 as yes, and the rest were no, you would have index 1 as on, and then index 2 as off, index 3 as on, and index 4 as on as well. And that would represent, for example, her 20 questions. So even though it says 13, you're looking at the bits that compose 13. So consider the problem of finding the best match for the client out of a list of prospective matches. We consider a match A for a client better than a match B if she shares more answers on corresponding questions with A than B. So pretty much, let's say you're on Tinder, right? And then you're trying to swipe and see who has the best match with you. This person, maybe they have certain attributes that you might like, and you share in common with them. You're probably going to take someone, all else equal, if they have more things in common with you versus somebody who has less things in common with you. And in this case, what we're going to be measuring whether or not they have in common is the answer to their questions. So let's say you ask somebody 20 yes or no questions, or you ask 5 people 20 yes or no questions. You want to pick the person that has the most matches with you. And the way that you can see who has the most matches with you in this sense is you can look at the underlying bits. So for example, let's say you have a number like 5, which is 101 in bitwise, or in bit representation. Let's say you had somebody who was, so this is you, and this is candidate number 1, candidate number 2, right? So let's say you have 7, someone who's a 7, or their number is a 7. And you have another person that is, actually, let me use a different number. Let's use 2. So this is 0, 1, 0. And then you have someone who's 7, which is 1, 1, 1. Actually, it would be something like this, I believe. So this would be 1, this would be 2, and then this would be 4. Okay, never mind. Yeah, just this. So in this case, who has more matches with you? It's not going to be number 2 because they literally have nothing in common with you. Meanwhile, if you take the other 2, 5 and 7, you're going to see that you have the most in common with this person. And common just means you answer yes and yes to the same question. So you have a common of 2. Meanwhile, this person has a common of 0. Who do you want to match with? So you're going to want to return the index, meaning you can say the name of the person who matches the best with you. So the whole idea that you're going to have to do is just iterate through all of the people and see who has the best. And as you find a better and better candidate, you store the index, which you can think about it as like the person's name that you're swiping through, right? So let's hop into what the code would look like. So this count function, I don't think they tell you what it does. Okay, so what it ends up doing, you don't have to understand this code at all. Just know when it says count and mask, it's just you pass in a number and it'll tell you how many things are on. So for example, how many bits are on in a number. So if we're trying to find how many matches you have with someone, you're going to want to take the bitwise and. So the bitwise and was essentially what I was doing here. So right here, you're going to do 101 and 111. If you take the and of this, you're just going to see where do they have things in common. So you're going to, wherever they have a 1 and a 1, it's just going to be 1. If it's a 0 and a 1 or 0 and 0, it's just going to end up being 0. So we're going to end up with 0, 1, 0, 1. And then we can count. This right here represents what they have in common, the two people. And then we can count what it is that they have in common with this function. So we're going to get 2 from this because they have 2 things in common. So that's very relevant. The whole reason you want to take the and is because you're trying to see what you have in common. So let's store best count. And then you also want to store the best index. So we can say -1. It doesn't matter. You're hopefully going to find someone, So for X, sorry, I use X. So you're going to iterate through the entire matches array. So these are going to be the people on Tinder, right? And you're going to have the count function. And like I said, you're going to want to count what you have in common. So that would look like clients. Let's just rename this. Let's just write you, right? Let's just rewrite this. Don't do that on the test, but you get what I'm saying. So you and matches of X. So this right here is going to say, okay, how many things do I have in common with this person I'm currently looking at? And pretty much if this is greater than what you've already found, like the best count you already have, then you're just going to want to say, okay, this is the person that I'm going to end up choosing. And the reason I did -1 is because, actually, we can even start them both at -1, is because at minimum you can have 0. So if you set it off at, or actually, if you set it up at 0, it'll end up just sticking to whatever given index you start at. So it'll just stay at 0 if you find nothing better than 0. But if you start them at -1, then it'll at least get someone who has nothing in common with you, which I guess it would be the same thing. But essentially, you would end up saying best count is equal to count of you and matches. So that's saying you found a better best count, and you're going to update the best index to be equal to this current person. So that's saying, okay, this person has more matches than the last person I was looking at that I thought had best matches. Let me consider this person and compare them against the next best person, if there is one. And at the very end, you're going to return the best index, which is going to say, okay, this out of all the people I've swiped through, this is the person that I think I fit with. So let's see what they ended up doing. So res equals 0, best equals -1. They ended up doing a for loop, and he did int temp 20 minus count of clients XOR. Okay, so this looks very different from what I have, but I assure you it's the same exact thing. So really what he ended up doing, notice how you have 20 questions total, right? So you have 20 questions total. But the thing with doing XOR is instead of finding what you have in common, it finds what you don't have in common. So the way I explained it to some people is, so the numbers that we had before was like, I believe it was 101, and then let's just see, 111. So if you take the XOR of this, the way I like to explain it to people is, let's say there's someone, I'm sure you all know someone who argues with you a lot, right? So whenever you find a bit, whenever that person finds something that they can argue with you on, that you two are polar opposites on, meaning you're a 0, they're a negative, or sorry, you're a 0 and they're a 1, or you're a 1 and they're a 0, they're going to want to argue with you. So you can think about it like that, where XOR is whenever there's a dispute, meaning there's something off, we're not on the same wavelength, set it as a 1. their person's gonna argue on that. Meanwhile, if you're on the same wavelength, they don't want to take that because then like they can't argue with you. So you end up with 0, 1, 0. And what they end up doing is taking the count of this. So they're gonna see how many things are on in this. So we have 1. And they're subtracting that from 20. So the whole difference with this whole strategy of what they're doing is they're taking the total that you have and subtracting it from what you don't have. So the whole idea is that you have two groups. You have two groups of have in common and then you have another group. Okay, what's going on? So not in common. And we can say that you have the total of 20 questions, right? So the total size of this rectangle is 20. And you can either have things in common or you can't have things in common, but they all have to add up to 20. So what they end up doing is taking the total size of the options, subtract one of these circles out, and that'll give you the opposite. So you pretty much taking, to find out what you have in common, the way they're doing it is they take the total things that could be in common, subtract out what is not in common, and then you're left with what is in common. So I hope that makes sense. In discrete, this is called I believe it's inclusion exclusion, and you're thinking in terms of the complement. So the complement is the opposite thing you're looking for. So sometimes it's easier to think of things not what you're looking for, but the opposite of what you're looking for, and subtract that from the total options you have, and that'll help you easily find out like what you have in common in this case. So that's pretty much what they ended up doing. I hope that makes sense. They just ended up looking at it from a different way.
I was gonna ask, I heard this year on the foundation exam, we're not having any backtracking. Is that always gonna be relevant to Bitwise?
No.
Okay.
It's never been used with Bitwise so far.
Oh, okay.
Yeah.
Because they said something about backtracking not being on this year's foundation.
Yeah, it wasn't on the one in January either, or the previous one. So backtracking is out the way. It's a CS2 topic. But I hope you guys got that and you understand why this is the same exact thing. This essentially translates into this right here. I guess Guhai just wanted to be fancy, but you know. But the whole best count and best index thing is all the same, and you would get the same answer, regardless of how you did it. Yep, so let's go on to the next one. And I'll let you guys try that out for a couple minutes. So there are a total of 25 cards numbered 0 through 24. We can represent a set of cards with a single integer by setting the ith bit to 1. And if the set contains cards it'll set it to 1 if the set contains card I, and setting the bit to 0 otherwise. So if we don't have the card, it's 0. If we do, it's just going to be 1 on the bit. So for example, the set of cards 2, 6, and 7 would be sorted as 196, since 196 is equal to 2 to the power of 7, 2 to the power of 6, and 2 to the power of 2, the sum of those. Now, two sets of cards are disjoint if and only if no card appears in both sets. So it's pretty much saying that they have nothing in common. So disjoint, I'm not sure how many people here have taken discrete. This was a pretty discrete kind of explanation, but you don't have to know it. But it helps to know the basic things of a set. So a set is kind of a collection of things. And for them to be disjoint, like it says, they can have nothing in common. So think of two Venn diagrams. For them to be disjoint, they cannot be like this. They cannot have this section of overlap. They have to be completely separate, meaning this has to be 1, 2, and 3, for example, and then 4, 5, and 6. But in the case that they both had 7, then they have like the overlap right here with 7. So this right here would not be disjoint. Meanwhile, this would be. So I hope you guys get why. And essentially, when they're saying whether or not the bits are on, the way you would represent that would be, for example, let's take the same case. So let's say this is set 1. Let's say this is set 2. This right here is not disjoint because they have these two things in common, these two cards in common. Meanwhile, if you had something like this, they would be disjoint because they have absolutely nothing in common. So that pretty much will tell you whether or not the things are in common. So there's multiple ways to go about this problem. There's one way where you can iterate through all the bits and check whether or not they are on. So pretty much, let's say you have these two examples, but I'm going to add on a number of bits, and then of course it's going to be up until 25, but this is going to be 0, 0, 0. Let's say this is 1. So we're going to see, assuming all of these are zeros, do they have 0 overlap? So let's see where they have ones. So there's no overlap here, no overlap here, no overlap here, no overlap here, meaning that they have nothing in common. And if they have nothing in common, then you're good. So there's multiple ways about going about this. You can iterate through all of the bits and check if they have anything in common, meaning is one bit of mine on and is one of their bit on? If that's the case, and it has to be at the same location. So in a case like this would completely invalidate it. So you would just return 0 at that point because they're not disjoint. So let's just do that way. So that's like the longer way. And then I'll explain the much shorter way to do it. So it says you have up until 25 cards. So actually, I'm just going to use I so you guys can see it easy because they're using I in the problem. So pretty much what you're going to check at every given point is the same bit. So how can we get the same bit for each set? There's two ways. We can either shift 1 to the left and check if a specific bit is on, or another way of doing it is shifting the number down. So shifting the number towards the right, and then that'll tell us whether or not that bit is on. So what that would look like is we can do set 1, and we're going to shift this I times. So this is one way to check if a specific, the ith bit is on in set 1. Another way to go about it is to do set 1 and 1 left shift I. So this is going to shift 1 all the way. It's going to move it I times towards the left. So pretty much what it's going to end up looking like is something like this. So let's say we wanted to check whether or not the second bit is on. So let's say this is set 1. So set 1, you would take 1, which is equivalent to 0, 0, 1, and you would shift it twice I times. So if we're at index 2, if we're looking at index 2, we're going to end up shifting it 2 times to the left, which is going to have it right here. And then you can take the AND of these two numbers, because if you shift 1, that's only 1 bit is going to be on throughout the whole number. There's only 1 bit on, so it's kind of like you're flashlighting on a specific index. Are they both the same? And then you're going to compare from that. So you can see whether or not they are the same at a given index. So if set 1 and 1 left shift I, if it does not equal 0, And then another thing you're gonna have to check is, let me move this over. It's gonna be very similar, just this opposite thing. So this definitely looks like a lot, but I'll go ahead and explain it. So we're doing the same flashlight technique on the same index in set 1. So we're just shifting 1 towards the left and seeing, okay, is the 0th, is the first, is the second, are they on? And if they're going to be on, the and of them is going to be non-zero. Because think about it, if you have two numbers, and so if you have two numbers like this, if you take the and, what do they have in common? Nothing, therefore it's going to be 0. So this is equivalent to 0 right here. So if it does not equal 0, that means that they have something in common. So if this does not equal 0 and this does not equal 0, that means that they have that specific thing in common between both. And in that case, you're just going to want to return 0, which means that you're false. Otherwise, if you don't find that, you're going to want to return 1. You are disjoint. So that's one way to do it. But then there's another extremely short way of doing this one, which I'll rewrite. And I'll explain to you why both versions work. So this is as short as it can be, really. So let me explain why that is. It's based on the same thing that I just meant about and. So let's say you have the same numbers again. If you take the and of this, you're going to end up with 1, 0, 1. And this number right here is 5. 5 does not equal 0, right? So since 5 does not equal 0, this, in terms of Boolean value, it carries a true. So any number that is non-zero carries a true value in terms of Booleans. 0 always carries a false. So pretty much you can say, for example, let's say you have set 1 to be equal to 1, 0, 1, and you have set 2 to be equal to 0, 1, 0. And you take the and between the two. So let's see what they have in common. So they have nothing in common, meaning this number is 0. So we're going to end up with 0, but then the whole point of me adding the negation is to say, if they're equal to 0, then we're going to negate whatever number this is. So if we negate 0, since 0 represents false, if you negate false, you end up with true. So why is that relevant? If we have a 0 and we end up returning true from this function, that means that we have a disjoint case. They have nothing in common. Otherwise, if they had anything in common, it doesn't matter if it's the very first bit, the last bit, the 31st, the 22nd, it would be non-zero. And like I said, any number, let's say 64, if you do a negation on this, this is a true value. If you negate a true value, it'll return false. So this is the whole meaning behind doing this right here. It just takes what they have in common. If they have nothing in common, it'll be 0. And negating 0, since 0 equals false, negating false means true. So that's the whole idea of this disjoint. And this is pretty much what this function is doing, but in just one line. Here you're just stopping at the first bit that they have in common. They're both 1 between the two. Versus in here, you're just taking the full comparison between the two and negating it to see whether or not there's nothing in common. So yeah, this is what they end up having. So they did set 1 and set 2 equals 0. So this is the same exact thing. So This is exactly equivalent. It'll just negate it. So you could have also done it this way as well. It would still give you the same points. And in this strategy, they ended up shifting towards the right. So that was another strategy that I had mentioned that you can do. So again, this solution would also give you full points, but essentially what they ended up doing was they shifted this down. They shifted the number towards the right and took the and one of that. So that pretty much tells you, you shift down I times, and you're going to see if that bit that's now at the very front of your bit, or at the very front of your number, if that's equal to 1, you're going to do and 1, and that's going to tell you if it's on or not. So this is essentially equivalent to what they ended up doing. There's 2 ways to move through Bitwise. You can either do the flashlight, or I don't know what you can call this. You can call this the push down method. You just push everything to the right, slide it all to the right, versus flashlighting on one specific bit at a time. So these are the 3 ways of ending up doing it. And yeah, I hope that makes sense. If anyone has a question, let me know now before I move on to the next question. Okay, then. Okay. So this type of question, I'm not going to do because this is just like very, very basic. Do you guys want me to do this one or not? Just let me know, because this is just pure
Yeah.
number. Okay, cool.
You do it.
Yeah, I got you. Because most people want the word problems, but I'll do this one as well. So I'll just hop into this one so you guys can see how it works. So whenever you have or, so the first one is an or operator. So let's say you have this right here. If you take the or, which is just a vertical stick, no, that's the operator. Wherever you have a 1, it's greedy in the sense that wherever it can find a 1, it'll take it. So 1, 1, and then 1. So it took all the ones it could. Meanwhile, and let me just do some different examples. So if you had this right here, it would just be 1, 1, 1. And let's say you had 0, 0, 0, or let's just do this right here. Take the or of this. It's just greedy. It'll take a 1 wherever it can. And that's pretty much how or works. And we've already done that one like a couple times. So just go through it one last time. And of this would say, where are they both 1? Otherwise, just return 0, or just put a 0. So that's and. XOR, I already explained that one. It's like when there's an argument, the person wants to argue with you. So if you take the XOR of this, they see you have these things in common, so they're not going to argue about it because, you know, you guys are on the same page on that. Meanwhile, this, they're going to argue with you about this. So 1, 0, 0. So notice how they're the complete opposite, which is what I was explaining in that one problem where I was doing the rectangles and the circles. So that's XOR, that's and, that's or, and shifting to the left and shifting to the right. So you can think of shifting to the left. I like to think about it like this. You take whatever number. So let's say this is n, right? So we have n. And we're shifting this k times. So how can you rewrite this in terms of math? You can just rewrite this as n times 2 to the k. So I hope that makes sense. So let's say we had 4, and then we shifted it to the left by 1. This is going to be 4 times 2 to the 1, which would give you 8. And we can verify this is right because 4 is 2 to the 2, and this is still 2 to the 1, still you put an 8, and then we can do the exponent addition when you're doing multiplication. 2 to the 3 is equal to 8. So yeah, you can just verify that real quick. And yeah, you can do that that addition stuff because this is 4 is a perfect power of a perfect like result of 2, but that's the whole idea. So if you have 11 right here, for example, you would just end up doing 11 times 2 to the 2, which is just 11 times 4, which is 44. So that's how easy left shift can be. Right shift is a little more interesting. It's a little weirder because the whole thing is that you can cut off bits as you divide down. But I guess the best way you can think about that one is when you're doing a right shift, you're taking n, and instead of multiplying, you're just dividing it by 2 to the k. So this is the way you can think about it. So let's do the same example. Let's say we have 8, and then we shift it down by 1. This is going to be equal to 8 over 2 to the k, or sorry, 2 to the 1. And again, since this is 8 is a perfect number, it's just making it easier so you guys can see it. This is 2 to the 3 over 2 to the 1. And this is 2 to the 2, which is 4. And the reason I'm doing it like that is because 8 in binary is this. Meanwhile, 4 in binary is just this. So you can see how the shifting ends up working. It just brings it down by dividing by a power of 2 to whatever k is. So that's how all these operations work. And that's pretty much it for bitwise. As for doing the calculations, that's the annoying part, but let's go through it. And this is going to be the last bitwise. Then we're going to hop into summations. So I know everyone wants to see that. Okay, so before the timer runs out, go full screen. So let's start with the easiest one. The easiest one is this one right here, because I explained to you the formula. 11 times 2 to the 2 is equal to 44. Done. That's it. This one, though, is going to be a little weirder because we're going to have 330 divided by 2 to the 8. And 2 to the 8 is actually 256. So this is weird. So there are certain cases where it's going to be harder to tell what you're going to end up doing. So I'm just going to end up drawing all the bits out so you guys can see how it would work. So let's just start up from the top. So 43. 43, it's an odd number. So that means the very first bit on the right is going to be on. And the way I like to think about making these numbers easily is start off from the biggest number, the biggest power of 2 that can compose that number. So for example, 43, what's the biggest power of 2 that fits into it? It's going to be 2 to the 5, which is 32. Plus, and let's see, does 2 to the 4 fit? No, because that would be 16, and this would be 48, which is greater than 43. So now let's go down 2 to the 3. So 8, we're all good. Now, the smallest we can fit into 3 would be a 2 to the 1, which is just 2. And then the smallest we can fit between 43 and then 42 is just 2 to the 0. So that's going to give us the bits that are on right then and there. So what a lot of people end up doing, they'll just end up doing like the 1s and the 0s. That's confusing because like a lot of people, they might misplace or, you know, they might not count properly and they might not know it starts from 0 and whatever. So That's probably the harder way to go about it. This is the easier way because then you can verify, okay, is this right? So 32 plus 8, 40. 40 plus 3 is 45. So you're good there. Now let's do 93 or 96, sorry. So what's the biggest power of 2? That is less than 90, less than or equal to 96. It's 2 to the 6 because that's 64. If you times 2 this, you get 128. So that's not it. Plus, and can we fit 2 to the 5 in it? So 2 to the 5 is 32. So 64 and 32, if you add that, that is 96. So that's it. We're done. So that's way easier, isn't it? And just like that, we figured out what bits they have in common and what bits, like, you know, they might not. So let's just line these up. So they have, in total, when you have OR, you're just gonna see all of them that are on. So we're just gonna see, you're gonna put into a collection like all of these ones that they have in common. So 2 to the 6. So what do they have in common? They have 2 to the 5 in common. So that means we're only gonna take one of these, because if not, then we're gonna count it twice. So we're just gonna take one of these, and we only have 1, 2 to the 6. Because remember how OR works? If it's a 1 and a 1, like it'll pretty much just take one of each of the ones. So this would just be 1, 1, 1. And same thing here, you're not gonna wanna count it twice. And you're only gonna take one if they have the same, like the same power is in there. So we're just gonna keep going. 2 to the 3 plus 2 to the 1 plus 2 to the 0. And now we can just do the math. So this is 3, this is 2, this is 1. This is 8. 8 plus 3 is 11. This is 32. 32 plus 11 is 43. And look at that, look at that. It lines up because 32, 8, 2, and 1. So we have all those right here. And now we add what it didn't have, was 2 to the 6. So 2 to the 6, this is 64. And now we just add 64 between these two, and that's 107. So the answer for this one right here is 107. So yeah, I hope that helps right there with just calculating the numbers, because that's definitely the hardest and most tedious part of all this, just calculating the numbers. That's what
So
people
you recommend not converting to a binary and then doing all of that?
Well, unless they tell you not to do it, or unless they tell you to do it. Me personally, I think this is easier, because then, like, if you're messing around with ones and zeros, you might do it incorrectly. So this is like the way that I would go about it, to be honest. But you can do it however way you want to do it. Unless they tell you write the specific binary number, then go for that. But in this way, you can see that, one, your math checks out, and you're not just looking at a bunch of ones and zeros that, you know, you might have placed one wrong or whatever. When I used to study with my friends for the foundation, the first time when I took it, a lot of people would mess up on these because of, you know, one small error that they ended up doing. So yeah. So 117, 2 to the 6 is the biggest, 64, plus 2 to the 5, just 32. We're at 96 right now. So this is 96. So let's just see the difference between this right here. We have 21. So that means the biggest one we can fit right now is 2 to the 4. So that means now we're going to be at 5. So this is 16 plus 2 to the 2 plus 2 to the 0. So this is just minus 4 minus 1 is 0. So now we have everything in that number. Now for 74, the biggest one we can fit is 2 to the 6, 64 plus. So now we have 74 minus 64, that's 10. So we can use 2 to the 3, which is 8, plus 2 to the 1, which is 2, and that'll add up all to 74. So that was pretty quick for calculating these right here. And now we're taking the ands. So let's see what they have in common. So they have in common this. They have in common, yeah, just that. So it's just 64. Okay, so you can verify your math by just adding it up and whatever. So now let's do 76 and 49. So 76, 49. Two to the 6, which is 64. Plus the smallest we can fit is 2 to the 3, which is 8. And now we're at, so we have 72. So 76 minus 72, we have 4 left. So what can we use? We can use 2 to the power of 2. So that's 4. So now we're done with this number. And right here, we can see which is the biggest one that fits under 49. That's 2 to the 5, which is 32. Plus, what's the next one? So we have 17 left over. We have 17 left over. So we can fit in a 2 to the 4, which is 16. And we're going to be left over with 1, so 2 to the 0. So we are doing an XOR. So if we're doing XOR, let's see what they don't have in common. So what do they not have in common? They actually have nothing in common. So we would just add all of these numbers together. So since they have nothing in common, we would end up with 76 plus 49. And that would be 125. And this is the last one. So 330, and we're shifting it 8 times. So let's calculate 330. So what is the biggest power that we can fit into 330? Power of 2, that's going to be 2 to the 8, which is 256. Plus, and let's see what we have left over, just real quick. So this is going to be 44 plus 30, so I'm going to have 74. Okay, so we have 74, so we can use 2 to the power of 6, 64. Now we have 10 left over, so we can do this. There we go. So we can verify that. 10, 74, and this is going to be equal to 330. Okay, so now if we're going to be shifting all the way down, we know that this is the highest bit of 330. So if we shift it all the way down, let's see. So we're going to have a number like 1, 0, or actually 0, 1, 0, 0, 1. See, so this one is bit 1, 2, and 3. Oh, I messed up. You see, that's what I'm saying. You can mess up real easy if you're not careful. So 1, 3. So this step you don't really have to do, but I'm just going to show you guys how it's done. So 4, 5, 6. So this one would actually be on. And then 0, and then here. So this is 8. So all of these are on. And now if we shift it all the way 8 times, that means that the 8th bit is going to be right at the front. So for example, let's say we have a window, right? So this is our window. Whenever you jump out the window, whenever this number goes here, you lose. So let's do this 8 times. So we shifted down by 1, we lost this one. Shifted down another time, lost this one. So we've done it twice. 3, 4, 5, 6, 7, and 8. So that means all of this goes away. It's out the window. And now all we're left with is this number right here. And that means that the final answer is going to be 1 because these are the only bits on, meaning everything else is just going to be a bunch of zeros. And we're going to be left with 1 as our final answer. And I guess you could have been able to tell that by this right here, but I just wanted to show you guys the explanation. So this should be 1. So 107, 64, 125, 44. So let's see. Let's see how we did. Right on the dot. Now imagine you were doing this with ones and zeros. Me personally, I think this is much, much easier to do. Because once you have these, you can make sure your math is right, and then you can just do the sums right then and there. You don't, because the whole thing with keeping it in binary like this, yes, you can mix up, but then another thing is you have to write the number out correctly in binary, and then you have to go back and calculate it correctly in binary. Meanwhile, if you do it like this, you essentially have what it would look like in binary form with 5, 3, 1, 0, without having to put it in that form, and you have the sums that can make sure at every step of the way your math is correct if you do it this way. Because you're gonna know whenever you put 32, now the smallest, you're gonna have like a cap on the bit you can choose, and you're gonna always try to choose the biggest power of 2 you can fit into the remaining like balance until you end up with 0, and that's when you know you did it correctly. So yeah, I think you guys should do that for these type of questions. These are just like busy work, like very annoying questions, and yeah, you shouldn't lose points on something like this. So oh yeah, and look at this. It says 1 point each, all or nothing. If answer is binary, divide square by 2. So unless they ask for binary, I wouldn't do the whole process in binary. And even if they did ask, I would just do it at the very end, just like I did here, because it's easier to see. All right. So let's see if this is a short one. Okay, now we're just gonna hop into actually let me see. Okay, yeah, we're just gonna skip on to the next session because it's getting late. So summations. All right, so we're gonna start off with summations. I'll give you guys until 7:37, around 7, and I'll hop into this question. All right, so first things first, we have to take care of the inner summation. So there's this formula. Whenever you have something that is a number to the power of j, there's this formula on your formula sheet where so you have a summation I is equal to n. You have a value x to the power of n, or sorry, x to the power of I. It's going to be equal to x to the power of n plus 1 minus 1 over x minus 1. So this is just a formula on your formula sheet. Whenever you see this format, something to the power of like the main iteration term, then you're going to want to look at this formula. So let's rewrite this inner summation right here. So we're going to rewrite it to, and this n, we're just going to keep it to whatever value we have in this specific summation. So we wouldn't use n, we would just use I in terms of n instead of n. So we would have as this inner summation 2 to the power of I plus 1 minus 1. And then we're going to have x, which is 2 minus 1. But if you think about it, 2 minus 1 is 1, and a denominator of 1 we don't have to write. So we can just leave it like this right here. So we have this, and then inside, that's inside of this summation, the outer summation. And we can think about how we can rewrite this. So we can rewrite this the following way. We can split it up, right? So we can split this up. Now there's multiple ways that we can go about this. I'm going to do this right side because there's a pretty easy formula. This is a constant summation. So what will end up happening is you're going to take whatever your constant is, which is right here, C. You can label this C, this is your B, and then this is your A. So the whole idea is you're going to want to multiply that constant by the number of iterations you're going to end up doing. So since it's from A to B inclusive, you're going to want to do C times B minus A plus 1. So the top bound minus the lower bound plus 1. So that'll give you the inclusive iteration behavior. So you're going to count for it as many times as you really should. So that means you're going to end up with minus, and this would just be 1, which we can disregard anything times 1 as just itself. So n, which is the top bound, minus the bottom bound, plus 1. So this is just going to end up being n plus 1. So minus n plus 1. And in this summation right here, let me see how much time we have left. We have 3 minutes. Okay. So right here we have 2 to the power of I plus 1. Or sorry, not plus 1 down there. It's plus 1 up here. So if we think about what that plus 1 in the exponent really is, it's actually a multiplication of 2. And the reason you can get that is because if you do 2 to the I times 2 to the, or 2 times 1, or 2 to the power of 1, you can just add these values. So 2 to the I plus 1, and that'll give you this value right here. So you can end up bringing this out and rewriting it. So you can end up rewriting this as following: 2 to the power of 1 times 2 to the power of I. But this value right here is a constant. So instead of keeping it in here, you can pull it out to here. So let's just do that. So 2 to the power of I. Let me make sure I'm not running out of time. Okay, we're good. We have the 2 chilling on the outside. Minus n plus 1. So now we can use the same exact formula that we previously used, but now it's going to be in terms of n. So what formula am I talking about? It's this formula right here. So again, disregard whatever this n is. It's just going to be whatever summation we're applying this on, whatever the top bound for that is going to be the n. So essentially, we're going to go back down and we're going to see, okay, let's apply this formula. We're going to end up with 2 to the power of n, and then add 1 to it, minus 1, all over x minus 1. And x is 2, 2 minus 1 is 1, and denominator of 1 is, you don't have to write. So this is really what we're left with, minus n plus 1. So at this point, let's see what we can end up with. So 2 to the power of 1 times 2 to the power of n plus 1 minus 2. I'm just distributing this over. And minus n minus 1. So this is going to end up being, we're going to do the same multiplication exponent addition. So 2 to the n plus 2 minus n minus 3. So this should be the answer. And by the way, you can rewrite this as well. Like you can bring out a 4, and this would be the same thing as this right here. So it doesn't matter. You can rewrite it this way. So this should be the answer if I check my work. Assuming I did it correctly, but let's just go and see what the answer ended up being. Yep, same exact thing. So does anyone have any questions as to how I did that? So pretty much the steps involved recognizing that you can use this formula, which I'm going to show you right now. It is this one right here. Oh wait, they actually don't show you it here. I'm gonna have to message them about that. It's similar to this one, but this one's infinite, so they actually don't have it here for some reason. But the formula is the one that I showed you guys. So it was this one right here. This is a formula that pops up on many different foundation exam questions. It did it on this one, and for some reason it's not on the formula sheet, but commit this to heart. This is a very important formula. Like there's many questions, they might not even show you it, which they didn't here, where you can use this formula. And yeah, it can save you a lot of time and maybe not even be able to solve the question. So I recommend you guys to write this down. So I'll give you guys a couple seconds for that. But the problem involved using the formula, splitting, bringing out constants that we didn't need until later on, and then just combining the constants together once we plugged in all the formulas we had to do. Okay, so let's move on to the next question. Okay, so I'll give you guys a couple minutes. I'll give you guys until 7:30 as well. These ones will end up being quicker, but all right, so let's get started. Determine the value of the following summation in terms of n, and they give us a summation. So let's write it down. And we want to express it as a final answer as polynomial in the form of an squared plus bn, where a and b are integers. Okay. So first things first, we have a minus, a plus, or whatever. You have to split it. When I say plus or minus, I mean you have like an expression that you have to split up. Let's do that at the start. So we're going to keep the same bottom bound and top bound. So 4i plus 2n and 7i equals 1. Okay. So now at this point, there's two ways you can go about it, whichever one you want to start with. Me personally, I like to get the smaller ones out the way. So the smaller of these two, in terms of steps left, is going to be this one right here. This is the same case that I was mentioning where you have a constant, the CBA case. So for the constant, you're going to take whatever values in here. So you have a plus, and then whatever values in here times the top bound minus the bottom bound. So this minus this plus 1 for the inclusion of the top bound. And you see that this just cancels out. So we're just left with 2n. So 7 times 2n, that's good. Now on this side, one thing you can do here to further simplify, make it easy, is you can bring this constant out. Because the whole idea is, let's say you have 1 plus 2 plus 3. what you end up doing is multiplying by 4 on all of these. And instead of having this term inside, you can just multiply the whole sequence on the outside by that. So it would be the same exact thing as doing this right here. Because then you can just distribute and you would end up with the same answer. So that's why you can do that, for those that might not have known. So you can bring this out to n of I, and I equals 1. Now we can plug this into the formula, and the formula is pretty much whenever you have something where it's just a summation of I, you take n, which is your top bound, so it would look like n times n plus 1 over 2. And in this case, our n, meaning our top bound, is 2 to the n. So what that would look like is 4, which is our constant, times 2 to the n times 2 to the n plus 1 all over 2. And then we have this on the outside. Oh, I think I had, okay, I think I had exclude this back. So this would be plus 1, and then this just cancels out. I think I had erased it, but then I undid that. Okay.
They have a formula for that one.
Huh?
There's that formula is in the formula sheet for that one.
Oh yeah. This one is in the formula sheet. Yeah.
The other one is too.
Yeah. This one as well. The other one, the one that I had mentioned, the geometric one, is not. But yeah, these two are in. So you guys can look at that to see where I'm getting those from. And from this point on, we can divide out these two. So we can remove this 2 and remove this 2. So we just divide that out. And now we're left with 4. And remember, you can't lose this n. This n is still here. You just divided out the coefficient, the constant, to the n. So now you have 4 times n times 2n plus 1. And that's going to leave you with, let's do this inside part. So we're going to have 2n squared plus n times 4, 8n squared plus 4n. And then we got to remember about this up here, this whole rest of the expression. Plus 7 times 2n, that's going to give you 14n. Let me just check the time real quick, okay. And we're going to end up with 8n squared plus 18n. And this is our final closed form solution on this one. And now the next one is pretty similar, but it's a little different because we're not dealing with things in terms of n. We're dealing with a finite summation. So we're gonna have a final value at the very end. That's not just like this in terms of n. So let me just expand this so it doesn't go out of bounds and show the answer. Okay, so same process. We're gonna do a split because we have this expression. And I'm just saying this one's gonna be a little longer. So I'm gonna go a little quicker on this one, but hope you guys get it. Okay, and now we're at a point where there is a rule that you can use, and I'm not exactly sure what it's called. Some people call it index shifting. I'm not sure if that's like the same thing that I'm thinking about, but essentially now we're gonna split the summation, but it's not gonna be a regular split. We're going to sum out the part that we don't care about. So what do I mean by that? What I mean by that is, let's say you have a summation that does not start at 1 like the formula requires. So let's say we have something greater than 1. So we're going up until 3. Actually, let's do 5, and we're going from I equals 3. So what this summation is going to end up equal to is 3 plus 4 plus 5. But the thing is, there's no summation for something starting at 3. So what the rule actually looks like is you have some numbers. So let's just say this is 5. I equals 1. we can easily calculate this with the formula because the formula would just be n, which is 5, times n plus 1 all over 2. So we can easily calculate this one. So the whole idea behind this is, and this, by the way, is equivalent to 1 plus 2 plus 3 plus 4 plus 5. So this is what the summation is. Now, if we want to calculate this right here, the only thing that is keeping us from calculating 3 to 5 with this formula is that we have this right here. We have these terms that we have accounted for in the rule that they give us. So the whole idea is if you want to calculate the sum from 3 to 5 right here, you can calculate the entire range, this right here, but you can sum out or you can subtract out the prefix. So what do I mean by prefix? If you're interested in 3 to 5, sum out everything from 2 to 1. If you're interested in this case, if you're interested in everything from, so you have 100, 99, ... then you're going to hit 21. And then from here, you're going to have 20, 19, ... 1. If you're interested in this area right here, you're going to end up calculating the sum of all these elements, and you're going to end up subtracting out everything from this bound minus 1. So everything from here to 1. And that's going to leave you with the final sum of everything from 21 to 100 exclusively. So this is something that you should really understand why it works, because a lot of people, they'll just try to look at the formula, see like the steps and just try to memorize it, but it won't help you if you can't understand why. So I hope this helps you understand why you have to perform a split, and what that type of split would look like is this right here. So I'm just going to do it on the original that we were working on. Okay, well now I'm lagging real bad, but it's all the drawings. It's all the drawings I've done. Okay, so let's do this one right here first. So we're going to start from the top bound, set it equal to 1. It's going to be 1 minus what I had mentioned. So you're going to want to subtract out the prefix. So the prefix to use the formula would be from 1 to 20 inclusive. So that means for me to get from 21 to 100 inclusive, I'm going to subtract out this entire thing. So that means our summation is going to start from 1 and go up until 20 inclusive. So this is what I meant by splitting. It's not the regular splitting where you're splitting an expression like this right here. This is what I like to call like prefix subtraction, because it's the values before that you're subtracting out. So now we're going to use a formula, the constant formula. And yeah, if you think about this, if you're doing 1 times 100 minus 1 plus 1, it's just going to be 100. And same thing here. You're going to do 1 times 20 minus 1 plus 1. So it's just 20. So we're going to end up with this entire thing right here is just going to end up equal to 80. So we have plus 80, okay? So that's what we have on that side. Let me just erase some of this. So if anyone has any question, definitely let me know. Okay, so this should be about enough space as I need. Okay, so in this summation, we have a constant that we can end up bringing out. So what I'm going to do is I'm going to write this on the outside. And we know that here, since this doesn't start at 1, we're going to have to do the split. So this would have been the same thing as if I wrote another summation, I bring it out, and then I perform the split, but multiply the whole thing times 3. It's the same exact thing. So inside of here, I'm going to end up doing the same thing that I mentioned, the prefix sum subtraction. So I'm going to have 1. Okay, and now from here, just plug and chug. So this is going to be 100 times 100 plus 1 all over 2 minus 20 times 20 plus 1 all over 2. Okay, so let's see, what is this going to be? So we're going to have 3. We can put this all over 2, by the way. All over 2. And we're going to have 100 times 101 minus 20 times 21. So let's see. 100 times 101, that is going to be 10,100 minus 20 times 21, that is 420. Okay, so now let's simplify this out. So we're going to have minus 420. So we're going to do minus 400. That'll give us 9,700 minus 20. That's going to give us 9,680 over 2 divided by 3. So it's going to be 4,880, I believe, times 3. And remember the plus 80 all the way from up here. And now we can multiply this out. So this is going to be 12,000. Then we're going to have 2,400. Then we're going to have 240. And then we're going to add this plus 80 at the end. So I'll do that after. So it's going to be 1,4,640 plus 80. And that's going to give us 15,720, I believe. Okay, so let me just make sure I did all that math right. Did you guys get the same answer? Because I was doing that all in my head. Okay, well, I'm just going to whip out the calculator. Oh, see, I did do it wrong. 10 times 3, it was 1450. Okay, so this is just 14,520 plus 80. So it'd be 4,600 then. Okay. $40. I got 14,600. So let's see what the answer was. Yep, 14,600. That was pretty good math for in my head, but all right, so 14,600, and we got 8n squared plus 18n. So what do we get? 8n squared plus 18n, and yep, is this. By the way, remember on the FE, there's no calculator. So definitely, if you're not like the best at math, don't try to do this in your head. It's probably better to multiply it out. Yeah. Yeah, there's no calculator. So you're just gonna have to do these out. Don't do what I did here. Like no math. Just I was close, but not close enough to get the right answer, you know. So just off by a little. All right, next question. Okay, so let's start on this question. Okay, so given this summation, j equals 1. Yeah, it is long. So when I first set the time, I hadn't anticipated how long it would actually take. So yeah, you don't have to stay. The video is going to be posted, but all right. So let's get started. So first we have this inner summation. So let's notice how it starts at 1. Upper bound is n minus 2. The upper bound doesn't necessarily matter, but we're just taking a summation of j. So this is a formula that we can end up using, which is n times n. Okay, that's not an n plus 1 over 2. But of course, our n is going to be n minus 2. So we're going to have, we plug this into the formula, n minus 2 times n minus 2 plus 1 all over 2. So this is going to equal, if we just do this simple algebra right here, it's just going to be equal to n minus 1. So there we go. I'll just leave it like that. So n minus 1. So this is what we have inside of our summation. So now we have 3n I equals n. I'm going to have n minus 2 times n minus 1 all over 2. Okay, so here there's an interesting observation you can make is that most summations that can use some sort of rule, and when I say some sort of rule, I mean the rules that are tied to whatever this variable is, they typically feature this variable somewhere in the expression that's being summated, if that's a word. So if it's in the sum, then you can probably use some sort of formula, like it pretty much if it's a term in the sequence somewhere. But the thing is, there's no I here, and we know one thing: n is a fixed number because n cannot be variable. N is going to be where we're starting at, and n is going to be times 3 of where we're ending at. So really, this entire part is actually a constant. So normally you would think of a constant like something like this 1/2, like this right here. So you have a 1 here, and then you have this 1/2. You would normally like bring this out. But that would only be in a case where you had I somewhere in here. But in this case, there's no I. So really, and we know that n is a fixed, finite thing that's not changing. So really what you can just do is bring this entire expression outwards and bring it out here. So I know that's really weird, but that is actually something you would do in this case. And if you think about it, all of this was essentially times by 1. Everything is always times by 1, and it'll give you the same thing. So you leave a 1 in there, and now what you can end up doing is solving for this leftover summation. So this right here, what's it going to end up at? It's going to end up as something like, we're going to do the same prefix subtraction that I mentioned earlier. So set this equal to 1, 1, and then minus n minus 1. So this was the the bottom bound. So we're going to subtract that out until we hit I equals 1. Okay. And then now we're going to have 1 in here. So now we've broken this down, and now we just plug and chug formulas. So this is going to be is 1 times 3n minus 1 plus 1. So it's just 3n minus, and now we're going to have n minus 1 plus, or sorry, n minus 1 minus this one, the bottom bound, plus 1. So we can scratch this one out, and we're getting left with 3n, and then we just have this right here, n minus 1. So 3n minus n plus 1, because we distributed, and negative times negative is positive. So this right here is just 2n plus 1, okay? We have this 2n plus 1. And now we still have this term floating out. So now what we can do is we can bring this out down here, and we can multiply it. So essentially we're going to end up with, so we're going to do n minus 2 times n minus 1 all over 2. Oh, and also we have this term as well to accommodate. So let's calculate this. And this is just going to be algebra, like boiling and stuff like that. So let's do this first two right here. So n squared. And then we're going to do minus 1, then minus 1n. And then we're going to do minus 2n plus 2. So this is what we're going to be working with. And then 2n plus 1. This is all over 2. Now we're going to have n squared minus 3n plus 2. And now we're going to have 2n plus 1 all over 2. And let me just close this up so we don't see the answer. Okay, so now we just have to finish distributing this. So just to make this quicker, I like to use the expression with the smallest number of terms and then multiply from that one, this way, instead of doing like 3. It's the same thing, but it just makes it easier and quicker to process. So 2 times n to the 3, then minus 6n plus, minus 6n squared plus 4n. And now we're going to do the 1 against all 3 of these. So we're going to do plus n squared minus 3n. And now we're going to do 1 times 2 plus 2 all over 2. So let's see what like terms we can close up. So we have this like term and this like term, and then we have this like term and this one right here. So now we're going to have 2n to the 3 minus 5n squared minus n plus 2, and that's going to be all over 2.
It's plus n.
Huh? Oh, wait, is it? Oh, yeah, my bad. Plus n. There we go. So that's going to be the final answer. So let's see what we got. Yep, exactly that. So that's how you do that one. So if anyone has any question, let me know.
So we don't need to get it into polynomial form, right? We can just leave it like in the form up top.
Yeah. You can also leave it like that. So it says, what does it say? So also accepted is the polynomial multiplied out. So on the exam, just don't multiply it out since you guys are against time. I just did it, so you can see it, but don't end up doing that, because then you're gonna waste a lot of time. Like, you could have really cut it all off at this point right here. So you could have stopped and then not have to calculate all this stuff. So yeah, definitely just leave it in the simplest form. Don't leave it too simple where it's like, you didn't really do much, but just enough so they can see you can derive the final answer just like this. So, all right, I'm gonna do one or two more and then we are calling it a night, everyone. Okay. This one's a little different, so I'll let you guys work on it for a couple minutes and then we'll hop into it.
So, like, are you just screwed for this question if you can't get the first part?
Hello? Can you hear me? Okay.
Yeah.
So what I was saying was, give me a sec. I think I don't know, I got like a double feedback from somebody. Okay. So you were asking like if you don't get the first part, then you're pretty much screwed.
Yeah.
Okay, so you mean like if you don't get the first for loop, if you don't set that up correctly, then that's gonna mess you up for all the other ones, right?
Yeah, like if you don't have the summation formula correct, then like you can't do the closed form, obviously.
Okay, so for this type of question, I don't really know, to be honest, because it just kind of depends how lenient they are on their grading rubric. So if you get one of the summations, I guess since it's 3 points, it looks like they're judging you based on each of the 3 summations. So if you get the middle one right, then they might give you 1 point, and if you do the other 2 wrong, then you'll get just one point if you do just one right. So I think that's how it'll work. As for the closed form solution, if you do the summations wrong, then yeah, you definitely lose 7 points because then you're just going to have a wrong answer. You might not get all the points taken off, but a good chunk of it is going to be gone. So, but I'll explain how this one ends up working. So you have a for loop from 1 to n inclusive. So when we think about a summation, we know summations by default are inclusive. So let's write the very first one. I equals 1, and then we're going to have n. So this represents what a for loop is if n is inclusive. Typically, we do for loops that are not inclusive, and that would just look like n minus 1. So I hope you guys get that. So this is what we have right now for the first for loop. And as for the second one, we have a variable. This is I. We have k. We know that k is going to start at 1 for every summation or every for loop of I. At every iteration, we're going to start k at 1. So we know that is true. And it's going to go up until inclusive of I. Okay, and now we are in here. So this one doesn't look like the other ones, but it's kind of like they're trying to trick you in this one. So let's think about it. So k is going to start at 1 in any given iteration of I, but obviously k is going to be iterating up until I. So for example, let's say I is at 3, then k is going to start. So this is I. K is going to go 1, then 2, and then 3, right? So let's say when k is 3, we're going to set j equal to k. So j is equal to 3. And we're going to go while j is greater than 0. So if we think about it, what range are we going to be touching? And when I say touching, I mean like what range are we going to be going over in this while loop? So we're going to start at 3, which was k. We're going to go down to 2. So we're still greater than 0. We're going to go down to 1. We're still greater than 0. And then we're going to end when we hit 0. And we're not going to do anything in this 0. This is the terminating case. So if you think about it, even though we're going backwards, we can think of it as the full summation from whatever whatever K, like wherever you started at. Yeah, so j equals K up until 0. Yeah, so pretty much you're including the whole range from 1 up until whatever K is. So what that's going to look like is the following. So you're going to have J is equal to 1, because 1 is the last thing you're going to end up actually iterating on before you hit 0 and stop. And then it's going to start at whatever K is. So really, instead of going up in the summation from 1 up until K, you're really going down from K down until J, but it still represents the same number of things you're going to be doing. So this is just going to be 1, since we're going to be seeing how many times J minus minus runs. So it's going to run whatever this final answer is. So this is essentially what the summation would look like. So I hope that makes sense to everyone. That's what the summation looks like. And now to determine a closed form solution for this one, let's solve it. So first, let's solve this right here. So we have from J equals 1 up until K, and it's going to be a simple constant. So it's going to be 1 times top bound K minus the lower bound 1 plus 1. So this is going to end up being K right here. So now we're going to condense this and put this into the summation again. So we're going to end up with this right here. And then we're going to have K. And now we're taking the sum of K. This is going to be a familiar formula. So it's going to be equal to, let me just close this out. So this right here is going to be equal to the regular formula that we've always used. It's going to be n times n plus 1 all over 2. So this right here is going to be whatever our n is, which is going to be I times I plus 1 all over 2. And now we're just going to replace this in the summation. I equals 1. Now we're going to have I times I plus 1 all over 2. So if we think about what this is, we can rewrite this as n and then I equals 1. And we can pull out this 1/2, because notice how this is over, or it's all over 2, but this is essentially 1/2 times I plus 1. So we can pull out this 1/2 outside to make our life easier. And now what we can do, we can just distribute this. Now that we don't have the 1/2, we're just dealing with this right here. So we can just distribute it out. I squared plus I. And now from here, we have our 1/2 still. And now we have a summation that we can split up. So we have n, I equals 1, I squared plus the summation of n from I equals 1 to I. Okay. So now from here, there's 2 formulas we can use. So the easiest one to recognize is this one right here, which is just n times n plus 1 all over 2 plus, and then this formula, which is like really long. So let me go to I don't remember it. So just go here. It's this formula right here. So it's n times n plus 1 times n, or 2n plus 1 over 6. So let's just put that into the formula. all over 6 and 1/2. So let me make sure I put the formula down correctly. Yes. So now at this point, this is what we're dealing with, and we can multiply the whole thing. Actually, we're probably going to want to get common denominator. So we can multiply the top and the bottom by 3 on this one. So we can just do 3 or 3. You can probably leave it in this format and you'll get points. But I'll just end up going through it. So 3n times n plus 1 over 6. And all we can do is add this to this whole thing right here. Yeah, and I'm not gonna, multiply this out. It's a lot. And then now you can multiply this. This will end up with all over 12. And you can erase this 1/2. And that should be about it for this question. So let's see. All right, right on time. Okay, so let's see. So we got these 3 for loops right. That was good. And determine the closed form summation. So this is exactly what I had ended up with. And let's see what they ended up doing a little differently. So in my solution, I had ended up combining them into all over 6. Or sorry, all over 6 and then times 12. But if we just look right here, before I did this 3 over 3, we have 1/2 times n plus 1 times n plus 2 all over 6 plus n times n plus 1 over 2. So we are good there. We could have just stopped there. And yeah, they ended up just doing some further algebra to subtract it out, but you didn't have to do that. So yeah, this is about it. All you have to do right here. All right. So does anyone have any questions on that? Oh, okay. Okay, this is a nice one to end it at. It's nice and short. So I'm just going to hop into it real quick. So give a summation that represents the value returned by the following function in terms of its input parameter n, then derive its closed form. Something to ponder over. Int n. Okay, so they give us I, rev value is 0, and pow is 1. We have a for loop, and we're going to return ret val. Okay, so first things first, it's one for loop. So there's no nested for loop, there's none of that. Another thing to note is that pow starts at 1, but let's see why that might be relevant based on what the code is doing. So we're doing ret val plus equals pow, and at every iteration we are doing pow times 14. So what that's going to end up looking like is we're going to have, let's say n is 3. We're going to start at 0 and go up until 3 exclusive. So we're going to go 0, 1, and 2 because we're going from 0 and not inclusive of n. So ret val is going to be 1 at the start because pow is 1 plus 14 times whatever pow is. So pow was 1. So 1 times 14 is 14. Then the next iteration is going to be 14 times 14. So that's going to end up being, 14 squared, whatever that is. And then that's pretty much how the trend is going to go. So in terms of how the summation is going to look, we're going to go up until n minus 1. So n minus 1, remember, summations are inclusive, and we're not including n. We're exclusive of n. So that's why we're doing it like that. We're going to start at 0, And now we're going to have 14. And since we're multiplying times 14, since we start at 0, we're going to add that first. That's why I started this bound right here, because then 14 to the power of 0 is going to be 1. Then you're going to do 14, 14 squared, 14 to the third, or to the 3, and so on. So this is what it's going to end up looking at, the overall trend, meaning we're going to have I, 14 to the I right here. Now we're going to return whatever the summation of this right here is. So this is overall what it looks like. And then it
So
says
the return val plus equals pow doesn't mean anything.
no, this is exactly what it returns. This is rev val right here.
Oh, I see.
Yeah. So rev val, you're not calculating it. It's just you're calculating the runtime of what's going on. But the overall, what it's going to end up returning is, yeah, like a summation of 14 to the power of whatever value. So if we're going to solve this, I'm going to give the closed form solution. So we have that formula, the one that's not in the formula sheet for some reason. And it is n I equals, I believe it was 0. The one that they did. It might be 0 or 1. I'm pretty sure it is 0. And then it is x power of I is equal to xn plus 1 minus 1 all over x minus 1. So now at this point, we're going to end up with n 14 of n minus 1 plus 1, then minus 1 all over 14 minus 1. So I just plugged in, this is n, this right here is n, and just went from there. This is going to cross out. This is going to give us 14n minus 1 all over 13, and that should be our closed form. Now, as for part B, using big O notation, what is the runtime? So it's one for loop bounded by n, so we have O of n, and that should be the right answer. So 14n minus 1 over 13 and O of n. So the summation is right, and the geometric sum. So they did it a different way, but you could have also done the same formula that I did, because you end up with the same exact thing. 14n minus 1 over 13 and O of n. So that is that. So everyone, that was the final question. So today we ended up doing a bunch of questions, actually. We did a lot of stuff. So that's good. If anyone wants to use this website, the link is, it's in all the announcements that I make. So there's a website that I recently made. So definitely check it out if you want to study. And I hope this session helped. So yeah, I'm gonna call it a night here. This is gonna be on YouTube, on the SHPE UCF YouTube. Yeah, no problem. All right, see you everyone. Peace.